Welcome to the Chemistry, Biology and Math Revision Hub. Today we're doing the Pearson Edexcel International A-Level Chemistry Unit 6 for October 2023. Let's begin with the first question. Question 1 says a series of tests is carried out on a violet-colored solid A which contains 2 cations and 1 anion. Some solid calcium oxide is added to a spatula measure of A in a test tube and the mixture is heated gently. A pungent gas is given off which turns damp red litmus paper blue. They want you to give the name or formula of the gas produced in this test. Ammonia is the only alkaline gas that will show this positive result, so the gas should be ammonia. The next they say give the formula of the cation in A shown by this test. Ammonia gas should be coming from ammonium cation, so that should be my answer. In part B, alkaline solutions are added drop by drop to separate samples of an aqueous solution A until there is no further reaction. With dilute sodium hydroxide, a green precipitate forms which dissolves in excess sodium hydroxide, giving a green solution. With dilute aqueous ammonia, a green precipitate forms which dissolves in excess ammonia, giving a violet solution. So actually, the possible green precipitates will be those of nickel 2, chromium 3, and iron 2+. However, because here they said it dissolves in excess sodium hydroxide, that is going to be only chromium 3+. Also forming a green precipitate that dissolves in excess ammonia, that confirms chromium 3+ as the cation we're looking for. So they say state the types of reaction that occur when the precipitates dissolve. With excess sodium hydroxide, that is a deprotonation reaction, as some of the hydrogens from the water are taken away, producing hydroxide ligands. And then with excess ammonia, this is going to be a ligand exchange, as ammonia ligands are substituting the other ligands that were present. Next they say give the formula of the cation in A, shown by the tests in B. That should be chromium 3+ cation. In part C, an aqueous solution of A is acidified with dilute hydrochloric acid and a few drops of barium chloride solution are added. A white precipitate forms. They say give the formula of the anion in A, shown by this test. Anytime you see dilute hydrochloric acid accompanied by barium chloride, they are trying to test presence of a sulfate anion, and because a white precipitate formed, that is a positive test that a sulfate anion is present, and this is the formula. The next they say state the reason for adding the dilute hydrochloric acid. Dilute hydrochloric acid is added to react with any other anions that could interfere by forming a white precipitate as well. So I say the HCl reacts with any anions like carbonates. You could also say hydrogen carbonates that could produce a white precipitate and lead to false conclusions that sulfate anion is present. And in part D, they say suggest a formula for compound A using your answers in A, B, and C. From A, B, and C, we have seen there are 2 cations. There is ammonium cation and chromium 3 cation, while there is 1 anion. So I formed this compound first, a compound between ammonium and sulfate, which is ammonium sulfate, and a compound between chromium and sulfate, which is chromium sulfate. Because this is chromium 3, this is what we're going to form. And then we have 2 ammoniums, we have 4 sulfates and 2 chromiums. And then to get the simplest whole number ratio, I got 1 ammonium, 2 sulfate, and 3 chromium. So this is my answer here. So this brings us to the end of question 1. Let's continue to question 2. In question 2, compounds B and C are isomers with a molecular formula carbon 3 hydrogen 4O3. Compound B is a colorless liquid with a structure that we see here. Part A says name the functional group present in B. The functional groups present in B are the ketone functional group as well as the carboxylic acid functional group, so those were the 2 answers. In part B, a series of tests is carried out on B. Complete the observation boxes. The first part is 2 centimeters of aqueous sodium hydrogen carbonate is added to a test tube containing a small quantity of B. Because B contains a carboxylic acid functional group, when you add sodium hydrogen carbonate, carbon dioxide is going to be produced, and therefore my observation is effervescence. In the next part, they say a few drops of B are added to 2 centimeters cubed of acidified potassium dichromate 6 solution. The mixture is placed in a warm water bath. Placing this mixture in a warm water bath provides a temperature for the oxidation reaction. And if we go back here, we see this cannot be oxidized because it's a carboxylic acid group, and the ketone group cannot be oxidized. So the orange color of the dichromate will remain. So I say the orange solution is going to be the initial color, and then the final color is also going to be an orange solution. There is no oxidation that takes place, because there is no functional group to be oxidized. The next part says a few drops of B are added to 2 centimeters cubed of a solution of 2,4-dinitrophenyl hydrazine, which is Brady's reagent. They want us to write the observation. Brady's reagent is used to test for presence of carbonyl compounds, and since in compound B there is a ketone functional group, an orange precipitate is going to be formed due to presence of a ketone. And next they say a few drops of B are added to 2 centimeters cubed of Fehling solution. The mixture is placed in a warm water bath. Because we are using Fehling solution that contains copper 2+, initially the solution is going to appear blue, and the final solution it's going to be blue as well because there is no aldehyde functional group that is going to be tested by Fehling solution. In part 5, they say a few drops of B are added to 2 centimeters cubed of solution of iodine dissolved in aqueous sodium hydroxide solution. This is the iodoform test. They say the mixture is placed in a warm water bath. Here the observation, if I take you back to the structure B, we can see it has a methyl ketone, and this methyl ketone is going to give a positive test in the presence of sodium hydroxide in iodine, so yellow precipitates are going to be formed, and that is a positive result, showing the presence of a methyl ketone. Then part C says compound C, which is that formula, is also a colorless liquid. C is non-cyclic and does not contain a carbon-carbon double bond. C has a significant lower boiling temperature than B. Since they're isomers and it has a lower boiling point, this is not a carboxylic acid. It could be probably an ester because carboxylic acids and esters are isomers. Then they say C does not react with phosphorus pentachloride, and this tells us there is no OH group. They say C reacts with Tollen's reagent to produce a silver mirror, so that confirms C has an aldehyde functional group. And this is true because B had a ketone functional group and aldehydes and ketones are isomers. They said draw the displayed formula of a possible structure of C using this information. The structure I drew had an aldehyde functional group as well as an ester functional group, but there are also other possible structures like this one here as well as that, so any of the three would give you the correct structure. So this brings us to the end of question 2. Let's continue to question 3. In question 3, they say this question is about ethanedioic acid, also known as oxalic acid. Traces of ethanedioic acid are found in many foods including spinach, fruits, nuts, and seeds. A group of students carried out an experiment to determine the percentage by mass of ethanedioic acid in rhubarb leaves. The first stage of the experiment was the extraction of ethanedioic acid. 319 grams of rhubarb leaves was chopped up and placed into a large beaker of distilled water. The mixture was boiled gently for about 15 minutes and then filtered. The solution was transferred to a volumetric flask and the volume made up to 1,000 centimeters cubed with distilled water and mixed thoroughly. This solution was labeled R. One student suggested that hexane should be used as a solvent rather than water. Explain why water is used as a solvent and not hexane. From the question, they're trying to extract ethanedioic acid, which is a dicarboxylic acid, and we know carboxylic acids can form intermolecular hydrogen bonds with water molecules, and the extraction is going to achieve a high yield. So I said because ethanedioic acid is soluble in water due to the formation of intermolecular hydrogen bonds with water. The second stage of the experiment was the titration of ethanedioic acid, solution R. 25 centimeters cube portion of R were placed in a conical flask and titrated with either aqueous sodium hydroxide or aqueous cerium 4 sulfate, which is that. The equations for these reactions are as we see. So in the first reaction, we have sodium hydroxide in a burette titrated with ethanedioic acid in a conical flask. And here we have cerium 4 sulfate titrated with ethanedioic acid. Again here, this is going to be in the conical flask. And they say cerium 4 ions have a yellow color and cerium 3 ions have a colorless color. For each of these titrations, describe how the endpoint can be detected, stating the color changes in each case. In this titration, because we are using sodium hydroxide and there is no observable color change, we will need a specific indicator. Since this is sodium hydroxide, we can either use phenolphthalein or methyl orange. So here I chose to use phenolphthalein, and the color change is going to be from colorless to pink because sodium hydroxide is going to drop in maybe an extra drop in the conical flask, and we'll have the indicator in sodium hydroxide creating a pink color. In cerium 4, because this is going to be in the burette, it's going to be yellow in the burette. Every time cerium 4 is dropped into the conical flask, cerium 3 is going to be produced and the colorless color is going to be observed. But in the end, an extra drop of cerium 4 is going to be released into the conical flask, and that will mean we're going to see a yellow color at the end point. So I said with aqueous cerium 4 sulfate, which is self-indicating, color changes from colorless to yellow. And then with sodium hydroxide, you could use phenolphthalein or methyl orange. And if you use phenolphthalein, the color will change from colorless to pink. Next, they say some of the students decided to titrate 25 centimeters cubed portions of solution R with 0.0400 mole per decimeter cubed aqueous sodium hydroxide. The mean titer was 20.60 centimeters cubed. They want you to calculate the percentage by mass of ethanedioic acid in this sample of rubber leaves and give your answer to an appropriate number of significant figures. They've given us the molar mass of ethanedioic acid. Now here I wrote the equation for the reaction one more time using sodium hydroxide. And this is the information for sodium hydroxide, and that is the volume for ethanedioic acid. So since I have this information, I'm going to use this to find the number of moles. So moles of sodium hydroxide will be concentration times volume, which is 20.6 divided by 1,000 times 0.04, giving me that in mole. Now using the mole ratio, the moles of ethanedioic acid are going to be half the moles of sodium hydroxide, which gave me that. But these moles are in 25 centimeters cubed because that is the volume used. However, if you look at the question, the sample was in 1,000, so the moles in 1,000 are going to be the moles in 25 times 40, because 25 times 40 gives us 1,000. So if I multiply this by 40, as we see here, I get 1.648 times 10 power negative 2 moles. Now the mass of ethanedioic acid is going to be the number of moles times the molar mass, which is 1.648 times 10 power negative 2 times 90, which is given to us here, the molar mass, and I get 1.4832 grams. So the percentage by mass should be the actual mass divided by the mass of the leaves, which was weighed, times 100, and this gave me 0.465% as my answer. In part C, ethanedioic acid is used in many laboratories. It is usually supplied as hydrated crystals, which is that, and dissolved in distilled water to make a solution. A technician makes 500 centimeters cubed or 0.500 mole per decimeter cubed ethanedioic acid solution by dissolving 31.5 grams of hydrated ethanedioic acid and making the volume up to 500 centimeters cubed with distilled water. Calculate the value of X in the formula of hydrated ethanedioic acid, and the formula is given. So here I try to write the equation. If we have this hydrated sample and all the water is removed, we're going to get the ethanedioic acid as well as the water. Here we will have X. So we're given the volume as well as the concentration of ethanedioic acid and the mass of the initial sample. So the moles of ethanedioic acid that would be produced is going to be concentration times volume, which is 0.5 times 500 divided by 1,000, giving us that as the moles of the ethanedioic acid. Now the mass of ethanedioic acid is going to be number of moles times molar mass. We have the number of moles here, and the molar mass is 90 from the question, giving us 22.5 grams. The next part is to find the mass of water. Since we know the mass of the original sample and we've calculated the mass of ethanedioic acid, we can find the mass of water by subtracting 31.5 minus 22.5, giving us 9 grams. So the moles of water are going to be that mass, which is 9 divided by the molar mass of water, which is 18, giving us 0.5 mole. And finally, the mole ratio of ethanedioic acid to water is going to be 0.25 to 0.5, giving us 1 to 2, and the value of X is going to be a 2. So this brings us to the end of question 3. Let's continue to question 4. Question 4, this question is about the nitration of methyl benzoate. The equation for the reaction is as we see here. So the procedure is as below. You weigh between 1.9 to 2.1 grams of methyl benzoate in a 50 centimeters cubed conical flask, and then slowly add 5 centimeters cubed of concentrated sulfuric acid to the methyl benzoate with swirling, and place the flask in an ice water bath to cool. Then place 2 centimeters cubed of concentrated nitric acid into the test tube. Cool the nitric acid by immersing the test tube in an ice water bath before slowly adding 2 centimeters cubed of concentrated sulfuric acid. Allow this nitrating mixture to cool. Then using a teat pipette, Add the nitrating mixture very slowly to the conical flask, ensuring the temperature does not exceed 7 degrees Celsius. Then allow the flask to stand at room temperature for about 15 minutes, and then pour the contents into a beaker containing some crushed ice. Impure methyl 3 nitrobenzoate will form. Then recrystallize the methyl 3 nitrobenzoate using methanol as the solvent. Then weigh dry crystals and determine their melting temperature. So the first question says a barrel of concentrated nitric acid has 2 hazard warning signs. We have this one as well as that. State the 2 hazards. This is corrosive and that is oxidizing. So these were my 2 answers. Next they say give a precaution to reduce the risk when using concentrated nitric acid. Assume that safety goggles and the laboratory coat are worn. Because concentrated nitric acid is oxidizing and corrosive, you should wear gloves. In part B, explain why the nitrating mixture is added slowly in step 4. The reaction is extremely exothermic and a lot of heat is going to be generated, so this could lead to further substitution reactions. So I say the reaction is exothermic, a lot of heat could be generated if added fast. At high temperature, further substitution reactions could take place and purification could be made hard. The yield could also be decreased. In part C, during recrystallization, in step 6, the methyl 3 nitrobenzoate is dissolved in a minimum volume of hot methanol and the hot mixture filtered. The filtrate is cooled and the resulting crystals filtered and rinsed with ice called methanol. State why methanol is a suitable solvent for use in the recrystallization of methyl 3 nitrobenzoate. The methyl 3 nitrobenzoate is very soluble in methanol at high temperature. That allows it to dissolve so that the insoluble impurities can be removed. And when you cool, it's not that soluble, so that it can precipitate and leave the soluble impurities in the solvent. That allows for better separation. And then next they say state the purpose of each of the filtrations during the recrystallization of methyl 3 nitrobenzoate. They carry out filtration when hot to remove the insoluble impurities, and they filter when cold to remove the soluble impurities. Next they say give the purpose of rinsing the crystals, stating why the methanol is ice cold. They use ice cold methanol so that any remaining soluble impurities on the crystals is washed off, and the ice conditions are to ensure that the dissolution of the purified crystals is minimized. In part D, 1.95 grams of methyl benzoate reacted with an excess nitric acid to form 1.51 grams of methyl 3 nitrobenzoate. So they've given us the molar mass of methyl benzoate and the molar mass of methyl 3 nitrobenzoate. They say calculate the percentage yield. So I begin with the moles of the reactant, which is methyl benzoate. This is going to be mass divided by molar mass, giving us 1.95 divided by 136, which we have here, giving us those moles. Since the mole ratio is 1:1, the moles of methyl 3 nitrobenzoate are the same. So the mass of methyl 3 nitrobenzoate is going to be number of moles times the molar mass, which we have here, and this is going to be the mass of the sample. I could write here in grams. So the percentage yield is going to be the actual yield. This was obtained through the experiment, divided by the theoretical yield. This is from the calculation, times 100, and that gave us 58.2%. Next, they say give one possible reason why the yield in D1 is less than 100%. There could be loss of solid, there could be further nitration reactions, meaning the purified sample is going to be lower or there is going to be a lower yield. It could also be due to incomplete reactions. This loss could be that some crystals were dissolved in the solvent and couldn't be precipitated out. So this brings us to the end of question 4. Let's continue to question 5. Question 5. A group of students carried out a series of experiments to investigate the kinetics of the reaction between hydrogen peroxide and iodide ions in acidic conditions. The equation for the reaction is shown. So this is the equation for the reaction. So the procedure is as below. You measure 10 centimeters cubed of aqueous sodium thiosulfate solution into a conical flask and add 5 centimeters cubed of aqueous starch solution and 25 centimeters cubed of distilled water. Then you measure 5 centimeters cubed of aqueous potassium iodide solution and 5 centimeters cubed of dilute sulfuric acid and add these to the mixture in the conical flask from step 1. Then you measure 5 centimeters cubed of aqueous hydrogen peroxide solution into a test tube. Then add the hydrogen peroxide solution to the conical flask, mix thoroughly, and start the timer. Record the time when the solution turns blue-black. Repeat the experiment, varying the volumes of aqueous potassium iodide solution and distilled water, keeping the total volume of the mixture constant. The first question says, explain the purpose of adding sodium thiosulfate solution in step 1. This is to react with the formed iodine so that a color change occurs when it reacts with a specific amount. Now this should be so that a color change occurs. Then in part B, they give us a set of results. We can see all this in the table. And on the next page, they say plot a graph of 1/T against the volume of potassium iodide. The key thing about graphs is choose a suitable scale and then put appropriate labels as well as units and plot the points in the right way. So all we were plotting was 1/T, which is these results here, and then these results here. So there is red or 1/T on the vertical axis and this on the horizontal axis. Put the right units, right labels, and everything is going to be okay. And the scale has to be appropriate. So since it's a rate versus concentration, kind of, because volume is corresponding to concentration, so it's a rate versus concentration graph, which is a straight line through the origin. So we can say this is first order with respect to iodide. So here they said deduce the order of reaction with respect to iodide ions using the graph and justify your answer. I say first order with respect to iodide ions because the graph is a straight line through the origin. And part C says give a reason why the concentration of potassium iodide solution is significantly lower than that of hydrogen peroxide solution and sulfuric acid. So in other words, the concentration of hydrogen peroxide and sulfuric acid are a large excess compared to that of potassium iodide, and this is done so that the hydrogen peroxide and sulfuric acid do not limit the rate, meaning any changes that occur to the rate are going to be due to the changes in the concentration of potassium iodide. So I say a significantly lower concentration of potassium iodide is used, while the concentration of hydrogen peroxide and the concentration of sulfuric acid is excess to ensure that the rate of reaction depends only on potassium iodide concentration. So this brings us to the end of question 5 as well as to the end of the whole paper. Thank you for being with us. Do not forget to subscribe. See you in the next video. Bye-bye.